Hi, welcome to the Preflight for lesson 32 to 35. And the first question is find and classify the critical point or points of x prime equals to x times y minus 1 and y prime is equal to 2xy minus y. So how do we do that? Well, the first step is to pause the video and try to do it yourself. Okay, I assume you did that. And now we're going to go through it together, see if we get the same thing. So for number one, step one, what I would do is find a critical point. Because yes, you could kind of guess, okay, maybe 5.52 or 2.5 or one of these could be critical point. But why not find the actual critical points? Because you might have another exercise where you're not given the critical points. So to find the critical points, you take the right-hand side and you set it equal to 0. And that comes from the idea that if you have a curve like this, the critical points of the curve are where the tangent line is 0. The slope of the tangent line is 0. That is a critical point. So look at what we're doing here. We're just saying, hey, if I only have a first order derivative here and everything else is on the right hand side and it's an autonomous and linear, well, non-linear actually, but it's unautonomous, then what I can say is that the critical points will happen when the slope in the x is 0 and when the slope in the y is 0. So that's what we're doing. When the slope in the x and in the y are 0, we can find some critical points. Now, if these two were linear, we'd have two solutions, two equations to unknown, we'd find just 1 point, an x and a y. However, these are non-linear, so we may find more than one critical point. So let's see. If I solve in the top equation, if I solve for x, so for x equals to 1 over y, with y not equal to 0, you just have to specify because y can be anything at this point. Then let's put it into the bottom. So then we would get 2x, well, no. Now we can substitute x with 1 over y, and then we have that other y. I'm just substituting x back into here. And then here we'd have minus y. So the first thing that we do is we take this away. And then we can solve for y. So y is equal to 2. And now that we have y, we can go back into x. So as long as this is not 0, because we said for y not equal to 0, it's not. So we don't have to worry about it. And now x is going to be equal to 1 over 2. So the critical point for this is 1/2 and 2. And that's going to be one of our critical points. So this is what we did for x is equal to 1 over y. Now, let's see here for y. So if y is equal to 0 here, then I would get 0 here. So let's say for y is equal to 0, let's input that into here. And if y is equal to 0, we'd get 0 x times 0. I just inputted 0 for y minus 1. Or in other words, 1 is equal to 0. Well, that's not right. So y cannot be equal to 0. And so this is going to be our only solution. So we can already say that this is not right because it's giving us two solutions, and this is not right. And another way to be more than sure would be to input, let's input 1, 1 into this. If I input 1, 1 into this, I get 0. And I input it here, I get 2 minus 1, which is 1, which cannot be equal to 0. So that's not a critical point. And let's input 2 and 0.5. If I input 2 here, 2 times 1/2 minus 1, well, that's equal to 0, so that checks. Now, if this checks, then it means we're missing a solution. Let's see. 2 times, we said 2 for x and 1/2 for y minus y, which is 1/2. Now we get 2 minus 1/2, which is 1.5, which is not equal to 0. So we know that those two are not critical points. Now, we also see here that they're trying to trick us with a 2 and a 5. We had and a 0.5. We have these swapped. So this cannot be. So we already know that this is the answer. But let's see how I would classify it if they didn't tell me. I would find the Jacobian 2. Find the Jacobian. So to find the Jacobian, what you want to do is you want to define, once you have the system in this form, and this is for first orders, for first order systems, you can write xy minus 1 is your p. Your p of xy is xy minus 1, and your q of xy is 2xy minus y. 2xy minus y. A pro tip, if this were to be distributed outside, it would be a little bit harder to take the derivative, which is what we're going to do in a second. But like this, the derivative distributes into each term, so you can just think of it as the derivative of this first term plus the derivative of the second term. So always distribute everything before you do this. And then the Jacobian is going to be a matrix. I'll do it in general terms first. It's going to be a matrix, right here, where the first row is going to have dp with respect to the first variable, dp with respect to the second variable. So the derivative of the function I defined as p with respect to x, and the derivative that I defined as p with respect to y. And you'd go on for as many derivatives or for as many dependent variables that you have. And this will be the same, but it will be with respect to x here, but for the function q, and this with respect to y. So if we now actually do it for our specific case, what we get is what? And I can put the equal sign here because I define p and q. So how do you take the partial derivative of p with respect to x? Well, you treat everything else as a constant. So if y was a constant, we would just have the exponent rule for the x, which would give us a 1, and multiply by the constant in front. So that first term would just be times y. And then here, there is no x, so the derivative of a constant is 0. So we would add 0 or just not write anything. Now let's do the derivative of the same function, but with respect to y. Now we're going to do the same thing, but now y is our constant. So here, we're going to take the derivative with respect to y. We're going to get an x that multiplies in front, because the derivative of y is 1, and the derivative of a constant with respect to y is still 0. So we add 0 or we don't write anything. We do the same process over here. So here in this first column, second row, we're going to take the derivative with respect to x. So here we don't have an x. So it's like having a constant. So that's going to be 0. But this term, we do have an x. The derivative of x is going to be 1, and then it's going to multiply by everything else that is constant, so 2y. And here, now we take the same function, and we want to take the derivative with respect to y. So in this first term, we'd get 2x. In the second term, we get 1. So 2x minus 1. And once you have this, you want to evaluate the Jacobian at your critical points. So evaluate J at the critical points. Critical points. And if you do that, what you get is, what is our critical point? Well, it is 1/2 for x and 2 for y. So if y is 2, we're going to have 2 over here. X is 1/2. And then we're going to have 2 times y, which is 4, and 2 times 1/2, which is 1, minus 1, which is 0. So we're just going to have 0 over here. Now, we find the eigenvalues for these. And the reason why we find the eigenvalues is because we can look at this system, and the reason also why we found the Jacobian is that we found a linear approximation for a system. Now, a linear approximation for a single variable, let's say for L of x, is going to be equal to my original function. So let's say f of, well, let's call it p, and you'll see why I'll call it p. Let's say p of the point where I'm approximating, because the linear approximation has to be local, plus the derivative at the point where I'm approximating times the shift by an amount equal to where I'm approximating. And let's say that we have another linear approximation here, and this is q times evaluated at the point where I'm approximating that, plus the derivative at the point where I'm approximating it, times y minus y naught. And these are the equations of a line, and these are assuming we have variables in only single variable functions. Now, if we had a function of 2 variables, then this would look slightly different. So this is the one variable case. If we had 2 variables, and I would encourage you to watch till the end, because this can be very useful in understanding what we're doing. If we have 2 variable functions, then what we do actually is we say that this would be the function evaluated at our 2 variables plus, now we can't really find a derivative of both at the same time, but what we can do is take the partial of that with respect to one of the 2 variables that's changing and evaluate it at x naught, y naught, and then have this shifted by x minus x naught, and then take the partial with respect to the other variable. I don't think I need this symbol. And then evaluate it at x naught, y naught, and shift it by that amount. And now, if I were to take this, it's going to be similar, but with the q, so I'm just going to copy it to save some time. And I were to put the q here. What do we get? Q, Q, and Q. Well, you notice that we can express this top one as a vector, L1, and probably I should put L2 here, and L2. And then we can express this one as another vector, as the vector P of x naught, y naught, and Q of x naught, y naught. And remember, these are just 2 constants, because X naught, Y naught stand for values that we are putting into these functions. And now this is the cool trick. Notice how we have X here, Y here. So what we could do, and notice how these are the same terms. So what we could do is we could rewrite this as Px of X naught, Y naught, and then Qx, so this would be now our coefficient matrix because all these X naughts, Y naughts are just constants. And I think I made a little mistake when I said they're just constants. So this is evaluated at a specific X, but the Y is not evaluated, right? Or not? Because we evaluate the, because when we take the Jacobian, well, let me just show you. So here then we have X minus X naught, Y minus Y naught. Okay? So look at this. If we just look at this, we can say, let's just take the derivative of this. Then I get L1 and L2 prime is equal to, this is constant, so this will go away, is equal to Px, X naught, Y naught, so all of that, which is the derivative of P with respect to X, the derivative of P with respect to Y, the derivative of Q with respect to X, and the derivative of Q with respect to Y. And then, where do we want to evaluate it? At X naught, Y naught. Each of those need to be evaluated at those, at that point. And then here, we'd have times that, which let's just say that it is let's just call it H. So this, we just called it H. So, if we